So in this video we're going to talk about gases and we're going to do a couple of calculations, calculating quantities, calculations involving gases. A couple of facts to start with. This one may seem quite surprising, but it is a fact. At the top here, 1 mole of any gas always occupies 24 decimeter cubed at room temperature and pressure. Okay, so what that's saying is when you have solids, different elements have different atomic masses, so they all they all weigh different things. That's not true of gases. Every gas, regardless of what it is, every single gas, regardless of what gas it is, always occupies the same volume if you have 1 mole of it. So that volume does change depending on the temperature and pressure of the surroundings, but at room temperature and pressure it's 24 decimeter cubed. Now that's a constant and that's given to you in the exam, so you don't have to learn it. So these questions here, very, very straightforward once you've understood this fact. What volume does 1 mole of helium occupy at room temperature and pressure? Answer, 24 decimeter cubed. It doesn't matter what gas it is. What volume does 1 mole of carbon dioxide occupy at room temperature and pressure? Answer, 24 decimeter cubed, because it doesn't matter what gas it is. All gases occupy 24 decimeter cubed at room temperature and pressure. And the final question, what volume does 1 mole of nitrogen occupy at room temperature and pressure? 24 decimeter cubed. Okay. Right, so we now have our mole formula for gases. So if you remember, for solids it was moles equals mass divided by formula mass. For concentration it was volume divided by 1,000 multiplied by concentration equals number of moles. Now for gases we've got this one. Number of moles multiplied by 24 equals the volume. And we have to learn this. You have to learn that. That's not given for you in an exam. You have to learn it. You have to learn all those three. The solids, the solutions, and now the gases equation. So, what volume does 3 moles of methane occupy at room temperature and pressure? Well, number of moles is going to be 3, multiplied by 24. 3 times 24, that's 72, I think. 3 20s is 60, 3 4s 12, yeah, 72. 72 units, decimeter cubed. And there's our answer. What volume does 0.25 moles of chlorine occupy at room temperature and pressure? Notice it doesn't matter what the gas is. Because all gases at room temperature and pressure occupy 24 decimeter cubed. So, number of moles, 0.25, 0.25. Multiplied by 24, because that's the volume of gas. The volume any gas occupies at room temperature and pressure, so a quarter of 24, that's going to be 6 decimeter cubed. So we've now got some questions to answer here about predicting how much gas is going to be produced, or indeed need to react with another gaseous reactant. These are calculating quantities questions, and you may be thinking to yourself right now, right, 3 stages to that, moles, stoichiometry, moles, but these are easier. Okay, these are easier. They confuse a lot of people because a lot of people read them and think they're not easy, but they are easy. Let's have a look at them. Okay, it says, assuming the sulfur is present in excess, what volume of sulfur dioxide is made from 5 decimeter cubed of oxygen? Right, so let's write 5 decimeter cubed underneath the oxygen. Okay, it says, assuming the sulfur is present in excess, cross the sulfur out because there's too much of that, therefore it's not going to play any part in the amount of product produced. And the question is, what volume of sulfur dioxide? So we're going to put a question mark under the sulfur dioxide. There's the sulfur dioxide. Okay, so it looks like a calculating quantities calculation, because it is, and normally we do moles, stoichiometry moles for solids and for solutions, but gases are different, and let me explain why. In solids, we have to do moles equals mass divided by formula mass to find out the number of moles of a solid that's present. However, here, 1 mole of any gas, regardless of what it is, always occupies 24 decimeter cubed at room temperature and pressure. So all we have to do here is stoichiometry. We don't need to do the moles. We just do the stoichiometry because all gases occupy the same volume. Now, there's a clue. There's a clue if you're thinking to yourself, is this a multi-stage calculation or a one-stage calculation? The clue is the number of marks that's available for the question. This is a 1-mark question, so it's only 1 stage involved. So I always look at the number of marks available. More complicated quantities calculations always have 2 or 3 marks available. This only has 1, so it's quite simple. Okay, so we need to look at stoichiometry here to answer this question. Now, there's no number present before the oxygen in the equation, so there is an invisible number 1 there. Remember, chemists are lazy. Okay, if there's no number present, there's always a 1 because we bothered to write oxygen, so there must be at least one of them. Likewise with the sulfur dioxide, there's a 1 present before the sulfur dioxide, so 1 mole of oxygen makes 1 mole of sulfur dioxide, therefore 5 decimeter cubed of oxygen is going to make exactly the same volume of sulfur dioxide because all gases occupy the same volume. So the answer is simply 5 decimeter cubed because this is a 1-to-1 ratio, a same ratio. Next one down here, again, equally straightforward. It's a 1-mark question, so it's a 1-stage calculation. Assuming the methane is present in excess, methane is in excess, cross it out. What volume of carbon dioxide question mark underneath the carbon dioxide, is made from 5 decimeter cubed of oxygen? There's our oxygen, 5 decimeter cubed. Okay, so now we need to look at the stoichiometry again. 2 moles of oxygen this time. 2 moles of oxygen make no number before the carbon dioxide, so 1. 2 moles of oxygen make 1 mole of carbon dioxide. So this is a halving relationship. This number here is smaller. Therefore, we're going to get less carbon dioxide produced, and we're going to get 1 is half of 2, so we're going to get exactly half the amount of carbon dioxide as we started with oxygen. So half of 5 is going to be 2.5 decimeter cubed. And they are that straightforward. 2 more on the next page. 2 more on the next page. Here's the next page. 2 more on the next page at the top there. You can have a go at those on your own. And let's just quickly have a go at one slightly more complicated question down here. Okay, in this one, it says, now can you convert mass to moles using a reaction equation? So the question is, what volume of hydrogen, so let's put the question mark under the hydrogen, what volume of hydrogen is produced when 28 grams of lithium, so let's put 28 grams underneath the lithium, is reacted with excess water, cross out the water, and we're not fussed about lithium hydroxide either, so we can cross that one out. So, with this one, we are given a mass of lithium, so this is a calculating quantities calculation as well, but this time we are going to have to do moles stoichiometry, so to work it out. So moles equals mass divided by, well, this is an atom, so we'll say atomic mass. So if you want to write formulas, I don't think anybody's going to object. So moles equals mass divided by AI. AR is the abbreviation for relative atomic mass. Okay, so mass of lithium, 28 grams. We know it's a mass because it's got a unit after it, grams. Atomic mass is found from the periodic table. So lithium is here, and the mass number is at the top there, 7. Okay, so 28 divided by 7 equals 0.25 moles. So we start with 0.25 moles of lithium. Stoichiometry now, so that's our next bit, stoichiometry. Let's just write out the part of the equation we need. Is 2 moles of lithium react to make 1 mole of hydrogen. There's no number before the hydrogen, so there's a 1 there. 2 react to make 1. So again, this is a halving relationship. So if we don't start with 2 moles of lithium, we start with 0.25 moles of lithium, so half of 0.25 is going to be 0.125 moles of hydrogen. Okay, and now we need to do moles again over here because these calculating quantities are moles, stoichiometry moles. So now that was our moles for solids. Okay, now we need this equation from the other page for gases now. So number of moles times 24 equals volume. So what was it? It was number of moles multiplied by 24 equals volume. Okay, so we have got 0.125 moles, 0.125 times 24. Should we stick that one in a calculator? It's an eighth of 24, so I think we can probably work that out and say it's 3, but let's do it in a calculator just to prove it. I have been known to get my mental arithmetic horribly wrong, so I always check it with a calculator. Times 24 equals 3. I was right. Always good to do it in your head and then do it in a calculator. And if the two don't tie up, then you just have to just double check it because it's so easy to make mistakes either with a calculator or in your head. 3 is not good enough on its own, of course, because the question says what volume, and we are working in decimeter cubed here. So it's 3 decimeter cubed. That's how we do those as well. 3 stages. Stage 1, moles. Stage 2, stoichiometry. And stage 3, moles. Stage 3 was moles for gases. Okay, so we have to pick the correct moles equation, depending on whether we start with a solid or a gas, or if the question involves solutions, with solutions.